Hello everybody, welcome back. Today we're going to be talking about using big O notation. So the basic idea here, we're going to be talking about how to manipulate expressions involving big O and other asymptotic notations. And in particular, we're going to talk about how to use big O to compute algorithm runtimes in terms of this notation. So recall, we said that f of n was big O of g of n if for all sufficiently large inputs, f of n was bounded above by some fixed constant times g of n. What this really says is that f is bounded above by some constant times g. Now, we'd like to manipulate expressions. We'd like to given expressions, write them in terms of big O in the simplest possible manner. So there are some common rules you need to know. The first rule is that multiplicative constants can be omitted. So 7n cubed is O of n cubed. N squared over 3 is O of n squared. This is sort of the basic premise that we had when building this idea, was that we wanted to have something that ignores multiplicative constants. The second thing to note is that you have two powers of n. The one with the larger exponent grows faster. So n grows asymptotically slower is big O of n squared. Root n grows slower than n, so it's O of n. Hopefully this isn't too bad. What's more surprising is that if you have any polynomial and any exponential, the exponential always grows faster. So n to the fifth is O of root 2 to the n. N to the 100 is O of 1.1 to the n. And this latter thing is something that should surprise you a little bit, because n to the 100 is a terrible runtime. 2 to the 100 is already so big that you really can't expect to do it ever. On the other hand, 1.1 to the n grows pretty modestly. 1.1 to the 100 is a pretty reasonable sized number. On the other hand, what this really says is that once n gets large, maybe 100,000 or so, 1.1 eventually takes over and starts beating n to the 100, and does so by, in fact, quite a bit. But doesn't really happen until n gets pretty huge. In a similar vein, any power of log n grows slower than any power of n. So log n cubed is O of root n. N log n is O of n squared. Finally, if you have some sum of terms, smaller terms in the sum can be omitted. So n squared plus n has a smaller rate of growth. So this is O of n squared. 2 to the n plus n to the ninth has a smaller rate of growth. So this is O of 2 to the n. So these are some common rules for manipulating these expressions. Basically, these are the only ones that you'll need most of the time to write anything in terms of big O that you need. Okay, so let's see how this works in practice if we actually want to compute runtimes using big O notation. So let's look at this one algorithm again. So we created an array, we set the 0th element to 0 and the first element to 1. We then went through this loop where we sent each element to the sum of the previous two, and then returned the last element of the array. Let's try computing this runtime in terms of big O notation. So we're just going to run through it operation by operation and ask how long it takes. First operation is we created an array. And let's, for the moment, ignore the memory management issues. Assume that it's not too hard to allocate the memory. But let's suppose that what your compiler does is we actually want to zero out all of these cells in memory. And that's going to take us a little bit of work. Because for every cell, basically what we have to do is we need to zero out that cell. We then need to increment some counter to tell us which cell we're working on next. And then maybe we need to do a check to make sure that we're not at the end. And if we are at the end, to go to the next line. Now, for every cell, we have to do some amount of work. We have to do something like do a write and a comparison and an increment. And it's not entirely clear how many machine operations this is, but it's a constant amount of work per cell in the array. There are n plus 1 cells. This is O of n time. Some constant times n. Next, we set the 0th element of the array to 0. And this might just be a simple assignment. We might have to load a few things into registers or do some pointer arithmetic. But no matter whether this is one machine operation or 5 or 7, that's still going to be a constant number of machine operations, O of 1. Similar to setting the first element to 1, again, O of 1 time. Next, we run through this loop. For I running from 2 to n, we run through it n minus 1 times. That's O of n times. The main thing we do in the loop is this. We set the ith element of the array to the sum of the I minus first and I minus second. Now, the lookups and the store, those are all the sorts of things that we've looked at. Those should be O of 1. But the addition is a bit worse. And normally additions are constant time, but these are large numbers. Remember, the nth Fibonacci number has about n over 5 digits to it. They're very big, and they often won't fit in the machine word. Now, if you think about what happens if you add two very big numbers together, how long does that take? Well, I mean, you sort of add the tens digit and you carry, and you add the hundreds digit and you carry, and you add the thousands digit and you carry, and so on and so forth. And you sort of have to do work for each digit place. And so the amount of work that you do should be proportional to the number of digits. And in this case, the number of digits is proportional to n. So this should take O of n time to run that line of code. Finally, we have a return step, which is a pointer arithmetic, an array lookup, and maybe popping up the program stack. And it's not quite clear how much work that is, but it's pretty clear that it's a constant amount of work. It doesn't become worse as n gets larger. So that's O of 1 time. So now we just have to add this all together. O of n plus O of 1 plus O of 1 plus O of n times through the loop times O of n work per time through the loop plus O of 1. Add it all together. The dominant term here, which is the only one we need, is the O of n times O of n. That's O of n squared. So this algorithm runs in time O of n squared. Now, we don't know exactly what the constants are, but O of n squared means that if you want to finish this in a second, you can probably handle inputs of size maybe 30,000. Now, depending on the computer that you had and the compiler and all of these messy details, maybe you can only handle inputs of size 1,000 in a second. Maybe you can handle inputs of size 1,000,000 in a second. It's probably not going to be as low as 10 or as high as 1 billion, but, I mean, 30,000 is a good guess. And, well, it takes work to get anything better than that. And so this doesn't give us an exact answer, but it's pretty good. Okay, so that's how you use big O notation. It turns out that occasionally you want